wasn't until 1902 when the first controlled flight in a heavier-than-air machine took place. The Wright brothers' glider was the third they built, and their breakthrough was three-axis control and the basis for the patent they obtained. They realised that flight in 3 dimensions demands control in 3 dimensions, namely control in the normal axis, or yaw axis as it's known, lateral axis or transversal pitch, and longitudinal axis or roll. How then to move in 3 axes and maintain stability in flight? You don't want to change direction. Here is how. Roll axis is controlled primarily by ailerons that are moving surfaces outboard on the wings. The rudder also has a secondary effect on bank. The Wrights used wing warping to achieve this. It is control of the other 2 axes that I want to talk to you about today. What is needed is a moving surface in the horizontal to pitch an aircraft up or down, and a moving surface in the vertical to yaw left or right. The moving surface will deflect airflow and cause an aircraft to react in the desired direction. The horizontal surface is the tailplane, commonly a stabilizer with a moving elevator. In the vertical, it is a fin and rudder. In the cockpit, moving the control column fore and aft moves the elevator, and feet pedals control the rudder. The Wright's Flyer had a bicanard in the front to control pitch and a rudder at the rear to control yaw. Other aircraft designs also have had canards. There is little stability with those, which is desirable in a modern fighter but not another aircraft. Placing both horizontal and vertical control surfaces at the rear can be thought of as being one end of a long lever, namely the aircraft fuselage. Forces needed to produce a movement need not be so large as the lever is long. Remember, it was Archimedes who said that with a long enough lever and a fulcrum on which to place it, I shall move the world. The main wing with a conventional aerofoil profile will have a small incidence, which is the angle the wing meets the airflow and gives constant lift. Without the tailplane, the aircraft would climb. So most aircraft have a tailplane with a small negative incidence to counterbalance this. The whole assembly, tailplane and vertical stabilizer, are known as the empennage. There are many different configurations of those. Clean airflow or slipstream over these control surfaces is desirable, and propeller wash or jet thrust over the empennage gives maximum control at low air speeds. At transonic and supersonic speeds, elevators are rendered useless, and so designers came up with stabilators or moving tailplanes. Aircraft that have lost vertical fins and rudders have not necessarily crashed, but the loss of some or all of a tailplane is usually fatal. Small planes often have rudder locks and elevator locks, known as gust locks, to avoid damage from strong winds when the aircraft are parked. Woe is the pilot who takes off without removing these before flight. A further refinement has been the fitting of trim tabs to rudders and elevators. These are small control surfaces employed to apply a force by using the slipstream. Trim is set in the cockpit and lessens the effort needed to move the rudder pedals or control column. For instance, if a pilot wants to descend, the control column is moved forward, directing the elevator to move downwards. If the pilot is using trim, the trim tab will move upwards on the elevator, and doing so will apply a force to cause the elevator to move downwards. The airflow across the elevator will be directed downwards, thus raising the rear of the aircraft, and so begins the descent. Trim is set when an aircraft is out of balance, such as to counter a tendency to turn, climb or descend. Before takeoff, setting trim is part of the pre-takeoff checklist. Before your next flight, have a look at the aircraft's tail feathers and appreciate the work that they do.